Hey everyone, we're moving on to the next question. So from your quizzes again, question 7, or quiz 1, question 7. This question is fairly straightforward. You're trying to prove that the, the pseudo-inverse has this following alternative form, right? You really just need to prove for one of them because the other proof is pretty much the same. So I'll just focus on one of them, in particular this one. And we will be using the SVD form. Right. So the first thing you should note is that assuming the SVD form of A is U sigma B transpose, we know that the pseudo-inverse actually has the following, SVD form, right? And should be fine as a kind of known result, right? So that's the left-hand side. So all you need to do is show this thing over here actually has the same form as this, right? So we'll just kind of plug things in at this point. So just kind of just go A transpose A, pseudo-inverse A transpose, right? But before I move on, right, I'll just focus on this A transpose A thing because we need to find its pseudo-inverse. So we'll just sub things in. A transpose, I'll just put it in the SVD form. So that'll be V sigma because this is a diagonal matrix, so it's symmetrical. U transpose, and this is just U sigma and V transpose plus. Right? Now, since the SVD form has these matrices U and V being orthonormal, right? That's part of the form of the SVD. That means this form over here, this middle thing over here, just becomes the identity matrix, right? Because the rows are linearly independent and they're also orthogonal to each other. So here you just end up with V sigma squared, because this is just I, so you just multiply the diagonals, and V transpose plus. Right? Now, the thing we note is that since this is also technically an SVD form, so as you can see here, these two individually are orthonormal matrices, right? Because that's kind of by definition, V is orthonormal, so V transpose should also be orthonormal. Kind of just follows through, and so that the SVD form of this should be, well, you transpose everything, but you add the plus thing symbol to the middle. Right, so what happens technically is this goes over here, and this goes over here. And then you just swap the transpose signs. Right. Oops. Now, the question is, what is sigma squared? Well, the pseudo-inverse of sigma squared. Over here, you need to realize that sigma squared is a diagonal matrix. Diagonal matrix. It's not necessarily full rank, but the only non-zero terms are along the diagonal, right? And a special property of the pseudo-inverse of this thing is that it's really just a reciprocal of the non-zero diagonal terms, right? So if you were to imagine, so let's suppose I'll just choose a simple example. Suppose sigma is equal to 2, 0, 0, 0. Or actually, no, I should add a third one, just kind of illustrate the point further. 2, 0, 3, 0, 0, 0, 0, 0. Right, pretend this is sigma. The pseudo-inverse of this is very easy. All you do is reciprocal the non-zero terms in the denominator or in the diagonal. 0, 0, 0. The zero terms you just leave alone. Right? So it's kind of like an inverse. That's why so it's similar to, that's why it's called pseudo-inverse basically for diagonal matrices, right? So it's very easy to find. So since the pseudo-inverse of the diagonal matrix is just the reciprocal of each of the diagonal terms, if you square the diagonal terms, if you square a diagonal matrix, it's still a diagonal matrix. So you can pretty much swap the order, right? So if you want to do this, you're going to have V sigma plus squared V transpose, right? Because if you imagine, so if you squared sigma squared here, this would be squared squared, and if you want to assign reciprocal of this, just do that. And it's the same thing as just squaring the matrix, right? Because it's diagonal, right? So we know the form of A transpose A, so we need to just sub it into this whole thingamajiggy. So we'll do that. A transpose A plus A transpose equals to, right? We just sub everything into the SVD form. So we sub in this first thing up here, so plus squared B transpose. And we remember what A was. A we defined to be U sigma B transpose. Well, we're interested in B transpose, so V goes over here. Sigma symmetric matrix, diagonal matrix, so it's fine. Right, just do that. These cancel out as it's orthonormal, and you end up with V sigma plus squared sigma V, oh no, not V, U transpose. Right? Now, since the pseudo inverse of a diagonal matrix is really just, well, essentially the inverse, you just reciprocal the non-zero terms. If you were to kind of imagine this sigma plus, right, it essentially cancels out because you just multiply diagonal terms, right? So if you look over here, if you did sigma plus, you would see that every term turns to be 0 because 2 times a half is 1, 3 times a third is 1, right? Everything else is 0, and 0 times 0 is 0, right? Because that's how you multiply diagonal matrices, right? So you can see that sigma plus just gives you essentially something similar to the identity matrix, right? So you end up with this. So V plus sigma, oh, that's meant to be U, whoops, U transpose. Now the thing is, this thing is very close to our diagonal matrix, but if you note this sigma plus thing, if you compare where it's 1 and where it's, well, non-zero, right, they match up, right? So essentially, if you were to multiply two matrices, all the non-zero terms will remain the same, right? And the zero term obviously disappears, right? Same thing anyway. So the ultimate effect is, in this case, you just end up with the same matrix, because these things just decompose to this thing over here. And this is meant to be a V, right? So that's pretty straightforward. And if you look back to kind of the result we knew from before to begin with, the pseudo-inverse of A has this following SVD form. You can prove it pretty easily. You just need to prove the four properties. It'll be fine. And you see that this thing over here has that same form. So hence, the pseudo-inverse of A can be expressed in this following form, right? A transpose. And if you want to do it for the other part, so proving it for, I think it was what was it? A transpose? A transpose A transpose plus, right? You pretty much do the same thing as this. It's pretty much the exact same calculation. Shouldn't be too bad. So I'll just kind of leave that for you guys to do. Right. That should be all for this question. Right. I guess the most important thing from this question to note is that the trick of the fact that for the pseudo-inverse of a diagonal matrix is really just a reciprocal of the non-zero terms along the diagonal anyway, and that leads to a lot of nice results. Right. Everything else kind of follows through because of that.